Hello everyone, my name is Andrew Kim and welcome to the second video of my AP Physics C review session. Now the first video was about RLC circuit, and I know that RLC circuit is actually the last unit of AP Physics C, but still I just made the video first because simply you guys had a test coming up. And also this video is going to be about E&M. And I know that it's the second last unit of AP Physics C, but I'm just backtracing it because I believe that you guys need help more on the later units because they're harder. So that being said, let's get started. Of course, by the way, I'm going to make videos for the previous units as well, the earlier units, so don't worry. However, one thing you would have to be worried is that I'm not going to make videos for mechanics because mechanics is simply way easier. And also, I make the videos for AP Physics 1. So if you really need help, then you can go watch those videos. Now, I know that AP Physics 1 and AP Physics C teaches different things, but still, AP Physics C and AP Physics 1 have the same concept. They have the same basic concept, but it's just that AP Physics 1 involves calculus and a bit more complicated situations. So if you're just lacking knowledge, lacking how the formulas work and stuff, then I recommend actually watching those videos. And now if you want more advanced deep knowledge, then I don't know, you can come to review sessions or you can come to Monday tutorings and ask our great officers and ministers. So let's get started right away. So first of all, this unit is going to be about E&M. And the first thing you will have to know about it is flux. Now, flux is basically measure of the number of electric or magnetic field lines or arrows passing through a surface in a given amount of time. So I would like to define this as simply how many arrows are going through in a given area that you defined. Now, in order to calculate this, first of all, you would have to use this equation. Now, this notation, this weird looking notation stands for flux. Flux equals to E times A times cosine theta. And I'm going to explain you why this actually works. E stands for the electric field, A stands for the area, and cosine theta is basically cosine value of the angle that the line perpendicular to your area that you defined and the arrow makes. Now, first of all, as I said, flux is basically how many arrows are passing through a given area. So of course, if the area is larger, the more arrows will be going through. Now think about it this way. I always use the dodgeball analogy when I explain flux. If two people are playing dodgeball, one person is extremely skinny and short, the other one is massive. His area of his body is extremely big. Then of course the probability that he get hit by the ball is greater. He get hit by the arrow, his area gets hit by the arrow is greater. Thus, his flux is greater. That is why if the area that you define is larger, then the flux is also larger. Now, the second factor you have to think about is E, or the electric field. Now, what is electric field? What does it mean when you say an electric field is stronger? Well, I would like to say that it means that the electric field arrows, electric field lines are more dense if the electric field is greater. Now, if we move this on to the dodgeball analogy, basically electric field or how dense the line is similar to the number of balls that you're playing with in a dodgeball game. Think about it. There are some dodgeball games where you play with only one ball, whereas there are some dodgeball games where you play with multiple balls, like 7 balls. In robotics retreat, we played with like 10 balls. If we have more balls in the field, then of course the probability that you would get hit by the ball would increase because simply more balls are flying towards you. The balls that are flying towards you are more dense. Now, what this tells you is that when the arrows are more dense, when the electric field is greater, then your flux would also increase. That is why you multiply electric field to the area, and that would be proportional to the electric field or to the flux. Now, the last component is cosine theta. Now, I hate memorizing this formula as flux equals to E times A times cosine theta because when you say cosine theta, people always forget what theta means. They know that theta is a representation of an angle, but they forget which angle it is. Even when I was taking the first take of this video, by the way, this is the second take. When I was taking the first take, I accidentally explained that theta is this angle, the angle that the arrow and the surface, the area makes. However, that's wrong. Beep. Theta is the angle between the arrow and the line perpendicular to your area. So it gets really confusing when you start thinking about this theta and cosine thingy. So instead, just think about it this way. When you have a dodgeball flying towards you, a dodgeball that's flying parallel to you isn't a matter. Think about it this way. You're playing a dodgeball and you just decide lying on a floor. It's going to be painfully hard to hit you if you lie on a floor. Well, of course, it won't be impossible in the real world because humans have volume. We're not just a flat piece of paper. So you will be able to hit. But compared to when you're standing, the area that you can actually hit decreases dramatically if you just lie on the floor. Think about it. You're lying on the floor and you want to hit him. You can only hit his feet, right? I mean, of course, humans have height, so you can just throw from above and you'll be able to form the angle. But if we were just living on a 2D place and the player actually just lies, then it would be nearly impossible to hit the person because the surface area that you can actually hit decreases compared to when he's standing up. Thus, what this angle tells you is that basically how perpendicularly the arrows are hitting you. If the arrows are hitting you perpendicularly, it's easier for the arrows to hit. But if you lie down and if the arrows fly parallel to you, then the arrows can hit you only when, in a very ideal situation, when the arrows actually go through your slightest part. So that is what cosine theta is telling you. Cosine theta is basically telling you that only the perpendicular component of your arrow actually affects the flux. No matter how big your area is, no matter how big your electric field is, if the electric field is formed in a direction that is parallel to your area, then you would have zero flux. That is why we need this cosine theta over here. Now, that being said, let's move on to Gauss's law. Now, what Gauss's law is saying is that basically, if you have a charge, whether it's a point charge, a line charge, a surface charge, and you define an enclosed area around it. Now, when you say enclosed area, it should be a perfectly enclosed area without any hole or without any leakage. For example, if you pour water inside it, there shouldn't be any water leaking out of your enclosed area because it's enclosed. Now, what Gauss's law is telling you is that basically if you define the enclosed area around a point charge or whatever charge, then the flux formed by this charge that is going out of this area, this enclosed area that you defined, would form a flux again. And that flux is literally equal to the charge in the middle that you're talking of over epsilon zero. Now, epsilon zero is a constant. It has a value of 8.85 times 10 to the power of negative 12. This is a constant. You don't have to worry. This is always the same at every single time. Now, what gets different is the flux and Q. But now, some people, now actually, this unit gets hard because up to now, I was talking about a flat, rectangular shaped area where the arrows are going through. But now I'm talking about this weird enclosed what area? Now that sounds kind of weird. Now you might even think if it's enclosed, it's a shape. It's not an area anymore. It's a shape with volume. How can that be an area anymore? Well, now I would like to use an onion analogy. I hope you guys know how onions look like. Well, if you look at the onion, you have the outermost layer. If you peel off the outermost layer of the onion, then you get the next onion layer. If you peel off that layer, then you get the next layer. And it just continues going on. It's like Earth. It's like you have the crust, you have the mantle, and you have all the components inside. It's like the Russian doll, you know, how you have the outer doll, and inside the doll, you have a smaller doll, and inside that doll, you have a smaller doll, and so on. It's like that. Although this enclosed area is enclosed and it seems like it has a volume, you're not looking at the volume of it. You're not looking at the inside of it, but you're just looking at the outmost, this crust, this thin layer, this area of it. This outmost area of the onion is the only thing that you're looking at, not the entire onion, but only that outmost layer. Now, what you're trying to do is, instead of this flat rectangular area, now you're looking at this curved area. Now you're trying to calculate the flux that is made between arrows caused by the charge inside and this curved round area. So that's what you're trying to do. And once you actually succeed calculating the flux, then that value would be equal to Q, or the charge that's inside your enclosed area, over epsilon 0. Now, then some people might ask me, then Andrew, how do you actually calculate this weird curved flux? Now, you have to think about it this way. What's interesting is there's no difference between this spherical model and this rectangular flat model. Because if you think about this rectangular flat model, every arrow, we're hitting your square, your rectangle, at the same angle. It's the same with the spherical model. Every angle that the arrow hits, every angle made between the arrow and your surface is always perpendicular. Now think about it this way. If you connect to random points on your sphere and the center of your sphere, then that line would form 90 degrees with the plane that's tangent to the surface at the plane, at tangent with the sphere. So now what I'm trying to say is that if you define a weird looking enclosed shape, for example, if you define like a human shaped enclosed field, now it's going to be painfully hard to calculate the flux because every arrow hits the surface, the area, at a different angle. However, if it's a sphere, then every point on the sphere are equally distanced from the center of the sphere, because that's the definition of the sphere, and also they're all perpendicular to from the center. So that is why you can simply use this E times A times cosine theta. Now cosine theta will be 1 again because they're all perpendicular. So basically what you simply have to do is multiply E, the electric field, times A. So that's it. A is the area, by the way. So the two more concepts you would have to know is lambda and sigma. Basically, the formula for lambda is Q enclosed over L. The formula for sigma is Q enclosed over A. Now, what these tell you is lambda is basically the line density of a charge, and sigma is the surface density of the charge. Now, what this is saying is that when you talk about density, it's basically about how crowded, how congested something is. And when you're talking about how crowded or how congested something is, it's basically the total divided by the area given. If there's more of total amount, if you have more charge at a same area, then of course you would have more charge, the charge will be more dense. If you have the same amount of charge at a larger area, then it means that the same amount of charge can be more widespread, thus less dense. That is why when you want to calculate a density, it's always the total amount over area or a given space. Now, when you're talking about a line that has a charge, does this line have an area? Does it have a volume? No, it only have a length. That is why in order to calculate the line density of a charge, you use the formula, the charge on the line over the length of the line. That would give you how much charge is spread. Now, sigma is a surface charge. That's why you do the same thing, but on a surface. Now, if you think about a surface, there is a length on the surface, but simply a length of the surface is not sufficient enough to tell you actually how congested the charge is on the surface. That is why when you calculate the total over the space given, you still use the same total. You still use the total charge on the surface, but instead of dividing with a length, you're dividing with this area of your surface. That's why you divide with A. Now, the reason why we sometimes use these density is because in some questions, they don't literally just give us what Q is. They don't just literally tell us, oh, the charge of this line, charge of this object is something. Instead, they give like an infinite line with charge, and they tell us that the density of the charge, the line density of the charge is, for example, A. And using this A, you have to actually calculate the amount of charge that exists in a given length of the line, and use this part, enclose this part, and use Gauss's law. So that's what I'm doing over here. You have a line, infinite line, with a charge density lambda, and what you're trying to do is you want to first define this length L with this density lambda, and define an enclosed area around it, and use Gauss's law. Now, some people might ask, Andrew, why did you define the area around it, the enclosed area around it, as a cylinder, not sphere this time? Well, that's because the only reason why I defined the enclosed area as a sphere over here is because when it's a point charge, then sphere is the only shape that makes every point on the surface equally distanced from the center, and also form a same angle, form perpendicular angle at every point on the surface. That's why I use a sphere. But when it becomes a line, it's not a sphere that has every point on it equally distanced from the charge. If you have a sphere like this, some points might not be equally distanced. I mean, look at these points. Look at these blue points. These blue points are literally on the sphere, whereas these green points are far away from the line with the charge. That is why you use a sphere whose every point on the sphere is equally distanced from the line. That is why this time we use cylinder. And it's extremely important to have all points equally distanced and all points form the same angle with the arrow coming out, because it's the angle between the arrow and each point that decides cosine theta, which is multiplied to E and A in order to calculate flux. So that is why this time we used a cylindrical surface. Now, the last thing about Gauss's law, and probably one of the hardest thing, is when we calculate the charge enclosed in a sphere. Now, there are two types of questions that can appear. First question, well, both types of question are going to ask the same thing. They're both going to ask you, what is the charge, or what is the electric field on a given surface inside a spherical object that's charged? Now, this might sound weird, but again, let's think about onions. You have multiple layers in onion. Now, what the question is telling you is that the entire onion has a charge of plus Q. Now, what you're trying to do is you want to calculate the electric field that's present in only the third outmost layer of the onion. Now, how can you do this? Well, the first question type is an easier question type. It's when the onion is equally charged everywhere. Now, when it's equally charged, basically, Q enclosed, or the charge enclosed inside this enclosed area, this enclosed surface, this enclosed third outmost layer of the onion, can simply be calculated by the total charge times the ratio of the volume. So the total volume of the sphere is, let's say, large V, and the volume of the area, the onion that's enclosed by the third outmost layer of the onion is, let's say, small v. Then basically, the charge enclosed inside the third outmost layer of the onion can be calculated as the total charge times the small v over large V, because that's the ratio of the volume. However, the second question type, it's a harder question type, and that is when the question asks the same thing, but the onion is not equally charged. In each layer of the onion, the charge density is different. Now, in this case, you can't simply use the ratio of the volume because each layer, each volume have different charge. So in this case, you have to use this equation, and this isn't really even an equation. I never memorized this equation. You have to think about it. Now, what you're trying to do is, first of all, what's the whole point of integrals? The whole point of integral is when you want to find an area or when you want to find a certain value, what you do is you slice this shape into infinitely small pieces and you calculate the value of each small piece and add all of them. That's the whole point of integral. Now, what we're trying to do over here is when each layer of your onion is charged with a different charge density, then instead of simply using the volume, the ratio of the volume to calculate the entire charge inside the third outermost layer, what you're going to do is you are going to divide this onion into infinitely small layers. You're going to add the amount of charge present in each layer of the onion because each layer have different amount of charge. They have different charge density. And that, using integral, is literally 0 to r. And what goes inside would be the charge at each layer. Now, what 0 to r indicates is it's basically saying the 0th layer of the onion with the radius 0, and you want to add all the way to the onion, the layer of the onion with radius r. And r stands for this length, the radius of the third outmost onion layer. So what this integral is telling you is that it's basically adding the amount of charge present in each layer of the onion from 0th layer all the way to the third outmost layer. And that is going to give you the entire charge present inside the third outermost layer of the onion. So that's how you use this formula, and that's the concept that you would need in your head. So that's it for the Gauss's law. But what's interesting is that Gauss's law is not the only law in E&M unit. You have another big law, which is Faraday's law. So let's talk about this as well. So basically, Faraday's law looks like this. D flux over dt, that's equal to dV times dA, and that's equal to epsilon, and that's equal to IR. So now epsilon 0 appeared before, and that was a constant. But epsilon is basically, it's another way of writing V, or the voltage. But when you say epsilon, it's not just any voltage, but it's a voltage induced. Now, I'm going to explain how voltage can be induced. Now, what Faraday's law is telling you is that, in other words, change in flux is the voltage induced to mitigate the change. So I just told you how I'm going to explain how the voltage is actually induced, right? Now, how it's induced is basically when the flux change, then what Faraday's law is telling us is that the voltage is induced in order to mitigate or cancel out that change. So that is how voltage is induced. So then our question is, how can a flux change? Because in order to induce a voltage, you have to first change the flux so that the voltage is induced to stop that change. Then how do we change the flux? Well, easy. We've just talked about what flux is. Flux can be dependent on E, the electric field, A, the area, and cosine theta, the angle formed by the arrow and your area. So in order to change the flux, we would have to change one of these three. So again, how can flux change? Area change or B change? Now over here, I didn't say E, but I said B, because again, flux is not a characteristic that's only present in E, or electric field. It's also present in magnetic field. And when we talk about Faraday's law, when we talk about the voltage induced by Faraday's law, it only works on magnetic field. So instead of the electric flux, now over here, we're looking at the magnetic flux. So instead of E change, we would have B changing. So how can we change the flux? We can either change the area or we can change the magnetic field strength. So let's first talk about area change. There are two ways that the question is going to change the area. The first way is basically you have a magnetic field and you're actually pushing this circuit, this area, this rectangular area inside the field. Now, when this happens, of course, the area of the circuit, the total area of your square, your rectangle, does not change. But this area where the magnetic flux is actually happening, where the arrows are actually hitting you, will change. So it's something like this. Again, if you're playing a volleyball, and when you're 100% inside the field, you can be hit by the ball more likely than when you're only halfway inside the field. I mean, of course, people can still hit you, but let's say if the body part that's out of your field doesn't count as getting hit, even if it gets hit by the ball. Now, if that's the case, then if only half of your body is inside the field, then the probability that you would get hit by the ball and actually get out, so hit validly, would decrease. Same thing. Even though the area of this electric the area of this surface, this rectangular circuit, does not change, still the valid area, the area that can actually be hit by the dodgeball, or the area that actually magnetic flux can go through, changes. It would increase if you're pushing the circuit inside the magnetic field, and it would decrease if you're pulling out the magnetic circuit. And of course, when circuits stay still, no change in area. Now, what we're looking at is we're only looking at the change in area. We're only looking at the change in flux, because if the only reason why voltage is induced is because your flux changes and you want to mitigate, you want to cancel out that change in the flux, that's why the voltage is induced in the opposite direction. Thus, if the circuit just stays, then of course there won't be change in area, there won't be change in flux, meaning that there won't be any voltage induced. That's why it's important to remember that the voltage actually be induced only when the circuit is moving, and not only when the circuit is moving, but only when the circuit is moving in or out of the circuit. When from the magnetic field, if the circuit is moving just inside the magnetic field, it's not going in or out of the magnetic field. If the circuit is moving inside of the magnetic field, there won't be any voltage made, because again, there's no change in area. All area is valid, and all area the arrows can go through. Thus, no voltage and current induced. Now, in these questions, how you can solve the question is that basically, again, you calculate B. Now, B will be given from the problem most likely, and you calculate delta A, or you calculate the change of area, because you want to calculate the change in flux. So you calculate the change in area, and that can be easily calculated by the velocity of your circuit entering the field, and use that information to calculate the amount of voltage induced, or epsilon. Now, if you have that voltage induced, that voltage would be equal to, what would be equal to? IR, Ohm's law. Always think about the classics. V equals to IR. Thus, the induced voltage in the circuit would cause I, or current. Now, some people might ask me, what about there's no R in the circuit? What if you're just putting in a circuit without any resistance? Well, you're stupid. There's nothing such as a wire without resistance. Every wire, even an ideal, unless it's an ideal wire on your imagination, all practical wires have resistance involved. Thus, if you push or pull out a circuit into a magnetic field, then there would be current induced by the voltage induced in order to cancel out the change in flux. Of course, it does not cancel out the flux. It doesn't mean that if the voltage is induced, the flux actually disappears. But what I'm trying to say is that simply it's acting towards that way. Now, another way the question can change the area is using solenoid, using coil rotation. So basically what the question would do is that it's going to rotate a coil. Now, of course, it doesn't necessarily have to be a coil. It can be a rectangular circuit that looks like this, where you have magnetic field going on, and you can rotate this rectangular circuit. Now, what's going to happen is similar to above, the area, the actual area itself would stay the same. Even if you rotate a circuit, the area is not going to change, but cosine theta would change. The angle between the arrow and your surface would change if it rotates, and that would cause the net area that the arrows can actually go through would change. So that is why the area can change, and using mathematics, again, you can calculate the voltage induced, and using the voltage induced, using Ohm's law, you can also calculate the I, or the current induced. Now, the last option, the second option to change flux is instead just changing the magnetic field. Now, when you change a magnetic field, you can't really change it physically. Like when you were changing area, you were changing it physically. You were pushing the circuit in, you were pulling the circuit out, you were rotating the circuit, you were doing dynamic things. But when magnetic field changes, you can't really do a lot of stuff with it. It simply changes under a given equation. For example, the magnetic field at a given time t is t times a. Or like if the question gets more complicated, it might be something like a t squared plus bt plus c, or something like that. But still, you don't have to panic. The only thing you have to do is use calculus. Just take derivative of this, and that will tell you the change in magnetic field at a given time. So using that derivative, you can calculate the change in the magnetic field and multiply that to your area and to your cosine theta, and that would give you the change in flux. Change in flux is equal to the voltage induced, and using the voltage induced, you can also calculate the current induced. V equals to IR, Ohm's law. So that's it. Honestly speaking, this unit is indeed one of the trickier units, and I hope this makes sense. Also, there are two big theories: Gauss's law, Faraday's law. Both of them are they're pretty complicated. They can actually go into very deep, and there's also calculus involved. But still, you've watched my video, meaning that you at least understand the most basics. So I hope you do well in your unit test, your AP exam, your mock, whatever. Thank you for watching my video, and don't forget to have a great day.